Okay, so we're going to look at the solutions to unit test 3, starting with the multiple choice questions here. So the first one asked, given these 4 representations of relations, which of the following is not a function? Now the answer was D, but let's take a look why. So the first one is actually a function, and this was meant to throw you off because you have the 1, 2 here and the 1, 2 here, and you might think, okay, well, you have 1, it maps to 2, and then it happens again, but really you're just repeating the same information. I mean, this doesn't really mean anything. So it's there to kind of throw you off. So indeed, if you just look at it as 1, 2, 2, 3, 3, 4, that is a function. In B, you will notice that all the shapes on the right-hand side, okay, all the x's, they all map to one unique color on the left-hand side to one unique color on the right-hand side, and this is indicated by the y. Because it's only one, again, that is a function. In C here, you have an equation which has a pinhole in it. Okay, so right here at 1, 2, you have a, empty space, but really it's kind of being removed in the sense that it's, being bumped down here. Now nowhere, let me get a vertical line here. Again, if I were to drag this vertical line, nowhere is it the case that, the line passes through 2 points, and especially over here, okay? You're passing through, this point, but there is no point here. Okay, so indeed, this is also a function. It passes the vertical line test. The last one is D, and if you saw it right away, you'd realize that this is not a function. If you were to graph this, it's a semicircle, if you recall. It goes like that, and then the negative part will go like this, which means bang. Okay, right here and here, I failed the vertical line test. This is indeed not a function. So that was your answer for number 1. For number 2, it asked which of the following statements is true. The inverse of any function is also a function. That's false. All functions have domains x belonging to the set of real numbers. That is also false. You can just take, for example, the root function. Obviously, that's not all real numbers. There's only the positive ones or non-zero ones. The set of non-negative numbers, not non-zero. The set here in part C consisting of Michael Cooch, Michael Whalen, Chris Wills, Alana Wills is a function. This is false because if you look at the Michaels in both, one goes to Whalen over here and one goes to Cooch. So that's not going to work. And lastly, just by process of elimination, all functions are relations. Well, yeah, that's a true statement. Okay, are all relations functions the other way? No. Okay, but all functions are indeed relations. Last one in the multiple choice, we're looking at the range of this absolute value function, and if I just kind of do a rough sketch, not caring so much about the vertical stretch about it, but okay, it moves right 2, moves up 1, and what matters is really the way it opens and where its peak is. So this function clearly opens down, okay, because there's a negative here. So my range is going to be basically everything below positive 1. So if we take a look at our choices, all that really is viable is part D here. So that is, let's take a look at question number 4, okay? We're given a function which is given to us in functional notation as a square root function. And notice that it gives us the range of this function to be greater than or equal to -3, okay? Let's look at what Jeremie did over here. He was trying to find the inverse of h, and let's kind of zoom in on his work here. So you'll notice first that he takes the original, replaces the h of x with the y, interchanges the two variables, x and y, and then goes about solving for y. And he does that by bringing the 3 over to this side, hence from negative to positive, and then squaring so that way he gets rid of the root sign. Now, notice that Jeremie, he intelligently noticed that, okay, if I square everything on the right, that means I'm gonna have to square this 2 as well. Okay, and that's where this 4 comes from. He's kind of doing a whole bunch of steps at once, but that's okay. He's swapping sides here, flipping this to that side and vice versa, dividing by 4 with the y minus 1, and what he's left with is x plus 3. Okay, and x plus 3 squared over 4, and he brings over the negative 1 to give him x plus 3 squared over 4 plus 1, and that is indeed his inverse. Okay, in terms of the domain of this function, if you recall from the notes, the domain of the inverse is the range of the original, and the range of the original is the domain of the inverse. Okay, the range of the inverse is the domain of the original. So, depending on what information you have, it's very easy to kind of read that off. So you'll notice that this here and this here are identical. The only difference is the variable listed. Okay. Again, I'll just reiterate that. The domain of h is equal to the range of h inverse, and the domain of h inverse is equal to the range of h. Okay, and that holds true for all functions and their inverse. Okay, let's move on to question number 5. So here we're looking at Julia's work. Again, very neat. She noticed that the function was given first of all as a graph, and we are applying these transformations here. Now she doesn't show her work, so I'm just going to kind of illustrate how maybe she got one of the points, and then the rest of them you can do by extension. But before we do that, let's just make sure we understand which transformations are going on here. So the most obvious one is the negative, which is the reflection in the x-axis. The next one is the vertical compression by a factor of 1 over 2. Then we have a shift to the left of 1 unit, and finally we're moving 2 units up. So we got 4 transformations going on, and let's see actually how that affects the graph. So one thing to keep note, by the way, this is going to kind of like flip upside down. So the general behavior, like if you look at the graph here, right, these kind of peaks and valleys, right, they're gonna flip. Okay, like this guy down here is gonna come up here, and then this guy over here is gonna come down at the bottom, and then this guy's gonna come up here, and it'll go something like that. Now I didn't draw it accurately at all, but it gives me an idea of what my final graph is going to kind of look like. Okay, I mean, I won't have, for example, anything like this. Let's say I won't have like something coming down and then up and then down and then up and then down. Okay, I need to have the same number of kind of vertices on my transform graph as I do on my original. So let's get rid of that and see how maybe she got one of these points. So let's take let's take this point over here. Okay, this one down here. If I kind of read it off the grid, it'll be 3, -3. So what does that get mapped to? Okay, where does that point end up once I apply the transformation? So the thing that helps is writing this using a mapping notation, and it's going to be what do we have here? X minus 1, and then we have -1 over 2 y plus 2. So I'm just taking this from unit 2, where we introduced this kind of mapping notation to tell us where each point goes. So I have 3, -3, and that'll take me to 2, comma. If I plug in -3 there, I will get 1.5 plus 2, which is going to give me what? 3.5. Okay, so my new point should be at 2, 3.5, and let's take a look. Here's the beginning, 1, 2, and 3.5, 1, 2, 3.5. Perfect. So this point went over here, and you can apply this to all the other points, okay? Namely, these ends of the lines, and find out where they go. And then once you're done, you just connect the dots and you have your transformed function. Let's move on. Question 6 here is given to us by Kelly Stokes. She identified that we are applying as an argument the value a plus 2 to our function. And there's our a plus 2. So we're going to square it, multiply it by 2, and then subtract 1. And at this point, it's quite straightforward. Okay, you'll notice that here, again, a plus 2 squared is a plus 2 times a plus 2, and this is the whole expression. And then this here is 2 times a plus 2 distributed. Collect like terms, and you end up with, basically another quadratic, but in terms of a. So that is what the value of f of a plus 2 is equal to. Let's take a look now at some graphs which you were asked to do. The first one is complements of Ella Ottey, and the second one by Victoria Lee. So the first one was a root function. You'll notice that there are a whole bunch of transformations going on here. Probably the most important one when it comes to a root function is, where does it start? If you recall, the original root function goes something like this. Okay, so where is the new one, the transformed one, going to start? And just by looking at the equation, you have a reflection going on here, which tells me, okay, this is going to open down. You have a shift on here. Okay, forget about the stretches, compressions, that kind of stuff, because it doesn't really have that big of an effect on the general behavior of it. But what do we have here? We have a shift, so we're going to go back 3 and up 4. So you can see that our function, okay, goes back 3, up 4. So yeah, it's going to look something like that. Of course, the details are in Ella's final graph, and the reason why she made it more detailed was obviously to get those 3 exact coordinates. Now, how you get those is, I think the best way is just to plug in various values of x. Okay, once you know where it starts, this here is the most important point. Okay, -3, 4. The rest of the points, well, just pick an x value, calculate it, and get your y value. Ideally, you want to do it in such a way that this ends up being a perfect square. If you can, great. If you can't, just leave it in radical form, and you have an idea where it is when you crunch it on your calculator. So those were the points she gave. All good. For the second one, which was a reciprocal function, a little bit of preliminary work needed to be done. Namely, you had to rewrite it in such a way that you could identify. Notice how I'm factoring out the 2. The b value in this equation here, and also the h value, which is how much it's shifted. So the reciprocal, again, the original goes something like this and like this. The new one is now shifted 3 to the right and 2 up. So you'll notice that in Victoria's graph, she has this line going like this, and this one going like this. And right here, these are the asymptotes. Remember, they're not part of the graph in the sense that, there's no points on these 2 lines, but they're probably the most important thing because they tell you how the graph behaves. And that, when it comes to reciprocal functions, is probably the most important detail about them. In terms of, the stretch going on here, any kind of that stuff, the x or y axis, it's so negligible, right? she was able to graph the general behavior of this function. And notice that, both her and Ella, they did put arrows on the ends because these functions continue forever in both directions. Sorry, well, this one in both directions, left, right, up, and down. Whereas this one here just continues, in a easterly direction. So those are the two graphs. The second one asked additionally for the asymptotes, and those are just the equations of the vertical and horizontal lines. So again, really important function, and it doesn't take much to sketch it once you know what the key features are to look for, and that is of course the asymptotes and the direction it is going in. In question number 8, we were given a absolute value function, and you were asked to graph it, both the original and its inverse. So, and with 3 accurate points. So the original, if you actually set it up properly ahead of time, you'll notice that it becomes this. Okay, and all I did was I interchanged the negative 2x and the negative 8, factored out the negative 2, and that way I can read a b value off of that. I have a plus 4, which means I'm going to move left. I have a plus 1, which means I'm going to move up. Because it's negative, that means I'm reflecting in the y-axis. And in the sense, remember, absolute value function reflected in the y, well, it's the same. It kind of reflects onto itself. This side goes here and vice versa. So what does this graph look like in our plane? Well, you can see here that Taryn, when she graphed it, she definitely got the most important point, which was the vertex, so to speak, kind of where the two sides converge. And then the other points here, the 3.5 and 2, okay, the negative 3 and 3, she probably just got those by plugging them into the equation. Okay, she plugged in a 3.5, a negative 3.5, she plugged in a negative 3 and got whatever the corresponding y value was. That takes care of this guy here very easily. And what about the inverse? Well, the inverse really is just interchanging, right? If I flip these, well, I have my inverse point, and that's actually going to be over here, okay? And I keep going, I interchange all of these points, okay? And they're going to map to, all these guys down here. But another way to see it, okay, the inverse is if you reflect it in this line here, okay, and let's see if I can do this. No, I was trying to rotate my page, but you can see how, well, maybe I can do it like this. Do another color. Just with white. Here's my original. Okay. Oh, not that. Do it like this and like this. Here's my original. I'm taking this and I'm reflecting it in this line. So you'll see it ends up being over here. Okay. Again, just think of, this line through, this line through the middle as like as a window. Okay. And everything on one side reflects to the other side. Okay. So you have this nice symmetrical behavior appearing in your graph. So that was question number 8. Question number 9 was a first thinking question, and it's actually deceivingly simple once you get the hang of it. And Olivia Salvo was certainly able to identify, what to do here. Basically, you're given this table of values, right? This guy over here. And you got to use that table to figure out, what all these values here are, okay, for each part here. Notice that it's only 1 mark, so it cannot be that involved, okay? So what does this mean? F of 1 over G of 1. Well, let's go to our table here that calculates F and G. So F of 1 means I'm going to replace the x over here with the value 1. And 1 is over here. Okay, and when x is 1, f of 1 is 2. In other words, f of 1 is 2. G of 1, which is the denominator in this question, well, g of 1 is 1. Okay, when this over here is equal to 1, we get g of 1 equal to 1. So when I actually do the division, that's just 2 over 1, or 2. Okay? What about for part B? Okay, well, I have g of 2. Let's go back to our table here. I'll erase everything. G of 2, here's the 2, is going to give me 3. So that's the first part. Okay, g of 2 is equal to 3. So g of 2 is equal to 3, and therefore f of 3 is going to give me the value I want. And what's f of 3? Well, that's just going to give me 4. Question C was probably the hardest one of these 4, just because there are actually 2 answers. But let's take a look at how it's done. So it says to find the value or values of C such that, g of f of C is equal to 1. So you kind of have to work backwards, okay? Let me write it down here. G f of C is equal to 1. So what value of f of C, or just what value here, period, forget f of C, I don't want to complicate things. What value, when g is applied to it, will give you 1? Well, if we look at our table, okay, g of 1 is 1. Yeah, okay. So g of 1 is equal to 1. But what that means is, okay, then f of c has to equal to 1. Because remember, this is what f of c is. And then you have to go back to the table again and ask yourself, okay, well, f of c is equal to 1. What value will give me 1 for my f function? And it turns out there are 2, both 0 and 4. In fact, check for yourself. F of 0 equals 1. F of 4 equals 1. And I'm just reading that off the table over here. Okay, so that's why this question has 2 answers for C, and they're both 0 and 4. The last one looks at the inverse, and I know there's no, G inverse function explicitly written, like in another column, right? Like G negative 1x. But if you remember what the inverse is, namely, just going the opposite way, you can pretty much get the value of, this guy over here. So how do we do that? Well, first let's get f of 4. So f of 4 is going to be this guy here, and that it's going to be 1. So f of 4 is 1, and that's why there's a 1 here. And now it's G inverse of 1. So let's go back over here. So G inverse of 1. G inverse goes from the range of G to the domain of G. So this is G inverse. And basically it's saying 1 goes to 1. That's why we have G inverse of 1 is equal to 1 down here. So there was question 9 for 4 thinking marks. Question 10 involved creating an equation that's not quadratic, for which the range is all y values less than 1. So just anything opening up upside down. I'll notice that George Merdano here decided to use the absolute value function. And, there's a lot of stuff here that is probably unnecessary, but nevertheless, he put it in, that's fine. What matters the most is this guy here. Okay, remember, this has to be less than or equal to 1, the range. So it has to, if this is 1 for y, it has to be below here, and it can be any function, okay, that is always below y equals 1. So he chose to use the absolute value function. It goes down forever. It continues. I mean, you could have used the root function. You could have used, what else do we have? it's kind of continuous. Semicircle, no, that won't work because it'll stop somewhere. Parabola, well, we can't use that. The cubic, we can't use it either. Reciprocal, we can't use. I think that's it. We got the absolute value and the root function. Those are the only ones that we have so far that enable us to have a range less than or equal to 1. Last thinking question, again, thanks to Ella, asked us to find the inverse of a rather peculiar function. It looks like it's a reciprocal, but it's not quite. It has a quadratic equation in the denominator, so it's not exactly what we're used to seeing. But let's see if we can take or find the inverse regardless. So she goes about, setting up the equation without the function notation, interchanges x and y, and we're off to the races. And that we want to, solve for y, isolate for y. Now, the most important thing here is probably identifying that this here is a difference of squares. Is a perfect square trinomial in the sense that it's, some factor times itself. So whatever that is, squared. And in this case, it's y minus 2. Again, if you want to convince yourself, you can just find two numbers that add to give you negative 4, multiply to give you 4. The numbers are negative 2 and negative 2. Okay, decomposition, you can use this crisscross method, whatever works for you. But once she got that, okay, she brought that denominator up to the numerator of the opposite side, divided by x plus 1, which is where she got this from, and then took the square root of both sides in order to eliminate the exponent 2. So you'll notice here we have an expression. It is plus or minus because you can have both a positive and a negative in your base when you're solving a squared equation, something like that. Okay, it can be plus or minus 1. And the last step was to just bring over the 2. Okay, so that negative 2 on the left became positive, and she made, she was very good in terms of the way she presented this, in the sense that that value was not, underneath that root sign. Okay, it was separate from it, and that's good. Okay, to avoid confusion, it's probably better practice to put any kind of constants in front of the plus minus, but really if there's this much space, then that's quite clear that it is not part of it. Anyways, the last step was just to rewrite it with the inverse notation, and that was it. Okay, she got the inverse of the function. Happens to not be a function itself, but that is the inverse. I did, by the way, include also a restriction because x cannot be negative 1. I mean, if we're going to be picky in the sense, what this function this relation allows, it's pretty much anything but negative 1. In this last communication question, we were asked to, using a specific example, explain why the inverse of a function is always a function is false. So this statement is false, and we have to explain using an example. Julia decided to, take the trusty parabolic function, the quadratic function, and just sketch some random points on the left-hand side here, and just interchange the points, the x's and the y's, and then graph it here on the right-hand side. Okay, so if the inverse of a function is always a function, well, she gave an example of a function. Okay, well, this quadratic, this is a function. The inverse is not. Okay, so it's false because she found an example that shows, that this statement cannot always be true. Okay, I mean, there are cases where the inverse is a function. For example, if I have this, okay, the inverse is going to be this. And yes, that is a function. But in this case, when I have a full parabola and I take the inverse, no, it is not a function. So that is not always true. Notice that Julia's work is very neat, very easy to read, and to the point above all. I love her diagrams. Okay, she does them neatly, legibly, and she doesn't get too verbose. Okay, I noticed some answers, we've noticed, myself and Mr. Dalmeda, that some of the answers in the communications section tend to get excessively long, okay, and there's no need for that. Okay, that's it, and that's unit test 3.